Thank you, Saula sir. So I will start today's session without any further delay, and yeah, here we go. Okay, so today is our second session of this digital system design, and what we are going to do today is we'll have these two parts again, like yesterday. We'll in first part we'll discuss how to design using combinational logic, and the second part would focus on Verilog. Okay, so yeah, you can say first part is theory and the second is practical. So let's see. Because we are talking about combinational logic, and most of you know what combinational logic is, but let's revise. Combinational logic is essentially any logic or any function that depends only on the present input, not on the past inputs. Okay, so your output would depend only on the current inputs. Whatever are the current inputs, that would determine what the output is. Okay, and all of you know that all these AND gate, OR gate, XOR, NOT gates, and all these MSI logics like multiplexers, decoder, encoder, they are all essentially combinational logic. Okay, and we have studied in our books in detail how to design these combinational logic, how to solve those Boolean equations, how to understand those Boolean algebra, various laws, like De Morgan's law, etc., etc. So also to simplify all these equations. But the question which I'm trying to answer today is slightly different. The question is how to design combinational logic. Okay, so if I want to design a combinational logic, then some input would be given to me, input specification, because since yesterday we are talking about specification, so somebody will specify that this is the circuit I want to design. Okay, so from whatever course we have done or whatever understanding we have, for combinational logic particularly, these are the either of these three inputs are there as an input specification. Either you write a Boolean equation, and then or you will write a complete truth table, or somebody will give you mean terms or max term, and then you would try to design your combinational logic. And how do you do it? See, these Boolean equations will have one-to-one mapping with your logic gates. So
जो कोर्स लगा है ना मैं उधर से कॉल आया.
Please, everybody mute yourself.
All the participants, please mute your mics.
Call.
All the participants, please mute your mics. Dr. Neeraj, मैं सबको mute कर रहा हूँ. आप आपको unmute कर लीजिए आप अपने आप को. Dr. Neeraj, अपने आप को unmute कर लीजिए.
Yes, yes.
Thank you.
Yeah,
thank you.
Sure. Okay, so now how do we take it from there? Somebody will give you a Boolean equation or a truth table or min term or max term. Then after that, what you typically do is you will try to optimize it using Boolean algebra, K-maps, or twin McLexy method, or multi-level logic optimization. So I'll repeat all these four names. Either you try to do it using Boolean algebra. Boolean algebra means you will try to use those De Morgan's law or merging of expressions, etc. Or you will use K-map to reduce the expression, or twin McLexy, or you will use multi-level logic optimization so that your final circuit is optimized. And after that, you give a final equation, and that equation could be implemented using AND gates, NAND gates, NOR gates, and OR gates, etc. Basic gates. So these basic gates will have one-to-one correspondence with your initial Boolean equation. So that's how it works out very well. So let's understand this particular point, that how do you take these input specifications in a more clear way. So I'm taking an example. Let me say somebody is giving you an input specification like this. Z is a function which is which can be represented like this. So whenever we are not writing anything, that means AND gate, A AND gate, B or C, again or B and A plus C bar, plus A B C plus A bar B C. So somebody is giving you this specifications. How will you go ahead to design or to materialize your digital circuit? So what you will do is looking at the equation, so most likely what first thing you will do is you try to see that can I optimize it using Boolean equations or Boolean algebra. So you will try to expand it, and after expanding it looks like something AB plus AC plus AB plus AC dash plus ABC plus A dash BC. Now when you see this, then what you observe is that this AB and this AB, they're all same, so essentially you can remove them. Now further you have AC as well as AC dash, because AC as well as AC dash are there, so C plus C dash will become 1, so you can effectively make it A. And further you can optimize A plus AB to A, and similarly A plus ABC to A, and this ABC plus A dash BC can become BC. So using this kind of a Boolean simplification, yeah, I know I have spoken it very fast, but you can do your homework yourself. Finally, the expression will become something like this. And then after that, you can realize using using circuits, you can say that B and C are being ANDed, and whatever is the output, you are getting an OR gate with respect to A and getting the output Z. Fair enough, correct? So somebody has given us a specification in form of this equation, and then we can further did using this Boolean algebra. So the challenge with this Boolean algebra approach is that it doesn't guarantee, there is no systematic way, it doesn't guarantee that whatever output you are getting is the optimal one. Okay, so there is a good possibility that you will miss out one optimization or the other optimization. Okay, so for example, when we were starting minimizing this, this whole expression will become A, but you might have forgot to combine A, B, C plus A dash B, C to become B, C. So there is a, and all these rules of Boolean algebra are complex. You cannot always, even though you can memorize them, but applying them would require certain tricks, which is not always there. So that's why we require some systematic method, much more systematic method to resolve these input specification, or so some Boolean equations are given so that we can minimize it and then finally realize the circuit. So one possibility is to expand it completely. So I'm again taking the same example. So we will try to expand it completely. Expand means that we'll try to write everything, all the terms in a complete expanded form, so that all the variables, all the terms have all the 3 variables present. Okay, in whatever form. So when we will do that, so you would be, because every term will have all the 3 variables. So for example, AB will become ABC plus ABC dash. Similarly, AC will become ABC plus AB dash C. So we will expand them, and when we will expand them, then this will become a canonical form, which we also know as sum of mean terms or a product of max terms. Okay, so this sum of canonical form or sum of mean terms or product of max terms, they provide a very good way to show a function, correct, or to describe a function. And because once this canonical form, there cannot be one function cannot have 2 canonical forms, it has to be only 1 canonical form. So although in Boolean equations we can write the same thing in hundreds of ways or thousands of ways, but when you write a canonical form, it is bound to be only one canonical form. So that's why this method of writing into canonical form will give you a standard procedure. Standard procedure for what? One, to represent your function, and second, that once you have canonical form, then after that the method of simplifying that canonical form is much more easy. Easy means that it is systematic and there is only one particular possibility. So let's say somebody has given us the mean terms. Now we know what to do next. because we have done this K-map so many times that even in the night, somebody will ask you in the dreams that please wake up and solve this. You will be able to do it. So again, the output using K-map would be the same which we did using Boolean equations or Boolean algebra. Incidentally, because we know those Boolean algebra equations and we have solved that correctly. Okay, so finally you can again realize the same circuit the same way. Okay, so now there could be other possibility also again to represent the same specification. So in that case, what you will do is you will try to instantiate this value of A, B, C to all possible values. So you will give A equal to 0, B equal to 0, C equal to 0, or and then A equal to 0, B equal to 0, C equal to 1. Means all possible combination of A, B, C values you will give, and you will enumerate all of them. And this particular method, and you will evaluate the function Z for all these possible values. This particular method where all the combinations of A, B, C's are given and Z has been evaluated for all the combinations. This particular method we call truth table. So for the same function, if I write the truth table, it will come out something like this, where you see the observation here is that these A, B, C values are all the combinations of them has been created, and then F is evaluated for all the combinations. Okay, so let's say the number of variables here are 4, then the total number of combinations here will become 2 to the power 4. That means 16 combinations has to be there, and for all the 16 combinations, I will evaluate F. Okay, so using this truth table, again now whatever values are 1, then corresponding mean term, we can say that the output is sum of those mean terms. Or I can also use this F dash. So wherever my F dash is 1, I can say my output is product of those max terms. Okay, so I'm not explaining what mean terms and max terms are, assuming that it is basic, so you know it already. Okay, so for this particular function, now mean term become 3, 4, 5, 6, and 7, and similarly max term will become 0, 1, and 2. So I can use any of these, either sum of mean terms or product of max terms to realize my function F. In mean terms, it would be and or combinations, and in terms of in case of max term, it would be or and and. And you also know that all of these things can be further designed using either NAND gates or NOR gates. Okay, so good, but there is, so I can summarize this whole approach like this, that either we will get a Boolean equation or somebody will tell me truth table. Now, if I'm getting Boolean equations, either I will do Boolean simplification using algebra, Boolean algebra, or I will expand them to create the canonical form, and finally I will have mean terms. And similarly from truth table also, I'll get these mean terms, and from the mean terms, I can use K-map or QM method to get the optimized expression. So similarly from Boolean simplification also, we'll get this optimized expression. Now, one question I would like to now ask that who will give me these Boolean equations or truth table? So far, if you are a student, then your instructor is always giving you this Boolean equations or truth table to solve and realize your combination logic. And if you're an instructor or if you're a lecturer, then you're looking at the books, and books is giving you all the combinations, that this is the things to be solved. But from where? If you have to design a combinational logic, design means you have to create your own. Then who is giving you these Boolean equations? Who is giving you this truth table? That's a good question. So again, the fallback is that it is coming from specification. And specification would always initially start in English language. Okay, so let me take one example that let's say some specification was given in English, then how do we do it? So let us say, yeah, this is what we will follow, that how will these Boolean equations or truth table would be created. Okay, so now Boolean equations are still fine, that we can create out of English or out of specification, but this truth table has certain keywords which I would like to emphasize now, which I would like to talk about. One possibility, one issue is that not all the combinations are permissible. What does it mean? That your system will say that I will not allow, if A, B, and C values are 1, all of them are 1, then I don't know what the output should be. I don't allow that. All of the three inputs cannot be 1 at the same time. Okay, so that is one issue. The other issue is that this is again the correlated from 2A, is that some of these inputs you don't know. Let's say if not permissible inputs come in, input combinations come, then you don't know what is the output. Okay, output state is undefined in those cases. So this truth table has this particular major challenge, that if I am trying to enumerate all the combinations, that in some combinations specification is not clear essentially. Specification does not talk about my English specification or my C specification, does not say that what would happen in those cases. So I'll give you a very quick example. So for example, you're writing a case construct in C++. In case construct, you're saying case 1 this, case 2 this, case 3 this, case 4 this, case 5 this. But if your input on which this case statement has been applied, your input does not belong to any of these 5 cases, what will you do? That's where C will create a default. Okay, so sometimes it doesn't even create that default. If the default is not created, nothing would happen. Okay, because the way C would be executed, it will go through all these 4 or 5 cases. If those 5 cases, none of those 5 cases matches, it doesn't do anything. Okay, but here when we are enumerating truth table, we are enumerating all the combinations. That means we have to be sure that what is the output at every place. Okay, so that's where in your mean term and max terms, don't care conditions will come. These don't care conditions are only for those possibilities where these input combinations are not permissible. Okay, so one more caveat with this truth table, that the complexity will be dependent on the number of variables. So as we said, if number of variables are 3, total number of rows are 8. If number of variables are 4, how many rows in this truth table? So you see this. How many rows were there? Here there were 8 rows. If number of variables are 4, then it would become 16. If number of variables are 10, then it's 1024. If number of variables are 20, then number of entries in your truth table, number of rows in your truth table would be more than 1 million. And if somehow number of variables are 50, then it would take number of lifespans, our lifespans, which is around 70-80 years, number of lifespans just to enumerate all those combinations or those 50 variables. And I can assure you that this 50 variables is not a very large number of variables. So those who are familiar with C, you don't care when you're creating a new variable. Okay, and if you see a complex system, number of variables could be in the range of 50, 100, 200, whatever. So what I want to emphasize is that if number of variables are beyond certain limit like 10, 15, 20, then even enumeration of all these values are not possible. Okay, which also means that if I'm not even able to enumerate all the values, so that means Will I be able to solve it for optimal solution? Possibly no. There is no way we can optimally solve this optimization problem giving a minimal expression. Number of variables are more than certain, like more than even 10. We don't know how to do it. Even for the variables, 10 variables, number of entries are 1024. That means so many mean terms are possible. And if I try to find the solution, this is exponential. And this particular problem is proved to be NP complete. Okay, so although we are studying these K maps and Kuhn-McLeod methods, what I want to emphasize here is that yes, they have certain limitations. The limitation is the number of variables are more, then you won't be able to find an optimal solution. You have to go for a non-optimal solution. So that was not a matter of discussion here, but I just thought to bring this point so that we can understand that whatever K-map and Kuhn-McLeod methods we study, they're more theoretical in nature and more like a pedagogy tool. Okay, so to make you understand that yes, optimization is important, and this is how we do it. So otherwise, in practice, in practical computers, we even settle for a non-optimal solution or a near optimal solution. Okay, so this near optimal solution, because optimal solution will take ages just to enumerate all the combinations and just to converge that which combinations to be taken. Okay, so the next question which we have asked earlier is that how to create this input specification, either truth table or a Boolean expression. So we'll take some example from here that let's say some English specification is given. So yeah, let's say this is the English specification. You should laugh at a joke if it is funny, if it is good in taste, and it is not offensive, or it is told in your class by a professor and it is not offensive. So you see, this is a English language, but here it is precise enough that we can make a Boolean equation just out of this English equation. How to go about whenever we are trying to create a Boolean equations out of this specification. So we'll try to identify what are the inputs and what is the output. So let us say here laugh is the output. So we would like to know when are we supposed to laugh. Okay, so if laugh is the output, what is the input? Joke, let's say, is not an input, but the properties of joke, let's consider them as input. So one input could be whether it is funny, the other could be whether it is good in taste, the other could be whether it is offensive, and another input could be whether it is told by a professor. That means there are 4 inputs. So inputs are F, joke is funny, T, joke is good in taste, O, joke is offensive, and P means it is told by professor. And what is the output? Output we are saying L, laugh. Okay, so if this is so, then we can go ahead and create an equation. We can say L is equal to it has to be funny, F, and it has to be T, and it has to be not of O. Okay, and plus, or it has to be either told by professor and not offensive. So I can say that my L is equal to F, T, O, inverse of O, or O inverse, plus or it is told by professor and not offensive. So this way, from English specification, we can try to find out what could be my Boolean equation. So that is one important source of my Boolean equations. Okay, and this source is quite important because when number of variables are large and when you are designing big systems, so this English specification comes very handy. Maybe I can tell you from where these specifications are coming. So whenever you are creating some interfaces, for example, you have this USB interface, HDMI interface, or if you have studied some communication, there's some protocols which are defined. So all these protocols, they're essentially written in English, and from those protocols, we have to find out that what are the conditions when a function would actually be 1. So those English specifications of standards, specification of interfaces, from there we have to extract out that what would be my input and output. So let's take more concrete and technical example. Let's say I have an IoT node which should stop if manual button is pressed or error occurred or no more data is there to process. Okay, so here again, what we are going to do is we are going to identify what are the inputs. Input here would be manual stop, error, or data. Okay, and the output is whether it node has to stop or not. Okay, so this is my input, and from after identifying the inputs, then it is straightforward. Then we can create an equation. So in this case, the equation is very simple, that it has to be M and E and inverse of T. That means there is no data. Okay, so this way we can create, we can think of creating Boolean equations from the English specification. And yeah, so I can summarize this whole method as like this. First, I have to identify inputs, outputs, and then identify what Boolean relations exist among these input and output. I have to be as precise, as accurate as possible, because if it is not correct, then all the next steps in the process will go haywire. So once these Boolean equations are there, then we know what to do. We are got. So we know that we can use minimization using algebra, using K-maps, etc. Okay, so this is how English specification can be converted. Now the other one. So one thing here, there is no tool which can convert English specification into Boolean equations. It has to be done manually. There is no other way. Okay, so yes, it can be done that if you convert this English specification into C++ like specification, then tools can take over. But from English specification, we have to do it manually. These relations has to be built manually. Okay, so the other possibility was how to create truth table. So for truth table, we have to see more different kind of examples. Like I want to design a truth table for a full ladder. So what I will do is I will enumerate all the combinations. So I have enumerated that ABC values would be 0, 0, 0, 0, 0, 1, 0, 0, and then I will calculate the sum and carry. So 0, 0, 0 will have a sum equal to 0. And carry equal to 0. Similarly, 0, 0, 1 will have sum equal to 1 and carry equal to 0. So this way, because now we are applying all the combinations to find out what is the function sum, what is the output of function carry. So the thing here is now the two output functions, the inputs are same, ABC, but the two outputs, one is sum, another is carry. And for each sum as well as carry, we can have a different function that is enumerating, that is describing that particular behavior. Okay, so let me take a little more complex example. Let's say I want to add two 2-bit numbers. My output is 3-bit number. So let's say my number is x0 and x1, and the other number is y0, y1. I want to create an output function. I want to add all of them. So the output would be, of course, 3-bit number, Z0, Z1, and Z2. If I want to do this, what I need to do is, again, I will enumerate all the possibilities of x0, x1 and y0, y1. How many possibilities would be there? How many inputs are there? Because there are 4 inputs. How many possibilities would be there? There would be 16 possibilities. Okay, so for the 16 possibilities, then we will find out what is the sum Z0, Z1, Z2, Z1, Z0. So I have created that table, and let's look at this quickly. So here, yeah, I have enumerated all the 16 possibilities, and then Z0, Z1, Z2, that has been calculated for all the input combinations by manually adding these two numbers. Now, what would be the next step here? I have to create 3 different functions. One for Z0, where input would be x0, x1, x2, x0, x1, y0, y1. Similarly, there would be another function for Z1, where again there would be 4 inputs, x0, x1, y0, y1, and there would be third function for z2. So I will finally have 4 k maps, one for z0, another for z1, another for z2. So and then I'll simplify all these 4 k maps to find out what would be the function z0, z1, and z2. Okay, so yeah, this is how we can create this. And yeah, one more example. So let us see this one. So here we want to create a truth table for 7 segment display. This is also quite a like the 7 segment display. Let us say this is doing it for to display not all the numbers, but only the BCD numbers. BCD numbers means 0 to 9. Okay, but interestingly, this 7 segment can be used to display much more than this. It can display all 0 to. It can be used for some of the other characters like A, B, C, etc. But right now, let's say it is being used to display only the BCD numbers. Okay, so here, just like this case, here I have to create 7 different functions to see what would be the value of when this A would lit. So, for example, let's say it is denoting the BCD numbers, that means 0 to 9. Then this A would lit when input is when your combinations input combination means x0, x1, x2, x3 is forming 0. Then A would lit. Similarly, if it is 1, then A will not lit. But in case of 2, yes, A would lit, and in case of 3 also A would be 1. In case of 4, A is 0. In case of 5, A is 1. In case of 6 also, 6, it depends on how you are writing 6, but let's say you are writing 6 like this, then A would be 1. In case of 7, it would be always 1. In case of 8 also, it would be 1. In case of 9, it would be 1. And let us say my numbers are BCD. In those cases, the combinations more than 9, like 10, 11, 12, 13, 14, 15, they will not result in anything. So you don't care what is the value of A. They are called incompletely specified functions, or as we were saying before, that these functions are you don't know. They are actually don't care conditions in your K map. And let's try to understand what a don't care condition mean. Don't care condition means let us say this 10 will come, and in the case 10 will come, you don't care what would be the output. It could be 0 or 1. So what you are essentially doing is you're trying to optimize your design so that it could be minimally it would have minimum cost, whatever values it will take for A. Okay, similarly, I have to write a Boolean function for all the LEDs, A, B, C, D, E, F, G. So that's why it is called 7 segment display. So for all these 7 segments, I am creating a different Boolean function. Okay, so and then after that, for each one, I'm trying to enumerate that which values it would become 1, which values of input it will become 0. Now, I can now summarize this creating truth table method like this, that first I will find what are the inputs, what are the outputs. And then I will enumerate all the inputs and write the for that input combination. Okay. Now, this further, the third step is minimizing the expression for each output. And your Boolean expression, Boolean equations would again represent differently for each output. That's very important. That there is no same function. All these functions will become a different different functions. For example, in this case, A, B, C, D, E, F, G, all these 7 will be different functions. Okay. So with this, I think now I can summarize this particular session, and what I can summarize is that we have at least learned how to create specification from English. I will not say completely, but yes, we have learned it quite a bit. And then the second is we also have learned that how to create specification from truth table, how to create truth table, and then how to convert this specification from to form a digital circuit. So that was an overview of designing a combinational logic. So now I would be open to questions, and so I'll set at least some 15 minutes. We can join again at 11. And during this 15 minutes, what I would like you to do is that these are the two questions. You can note them down, take picture of it otherwise, and you have to send the answers before 11 a.m. Okay. So before 11, you will write the answers. If you are able to send the answers before 11, I would be able to see whether they are correct or not. After that, I will not be able to see and respond. Okay. So yeah, you have the